Hello, and welcome to the November edition of the Cosmic Adventures Lecture Series. My name is Dr. Mindy Townsend. I'm the astronomer with Dudley at Siena, and this month I want to talk about one of the most brilliant and creative astronomers of the 20th century, Cecilia Payne, and how her work turned our knowledge of the stars on its head and changed the way we saw the universe. Cecilia Payne was born in 1900 in the little village of Wendover, England. Her father died when she was 4, but her mom saw that Cecilia was extremely gifted and encouraged her education at a time when that kind of thing was not typically done. She was a very precocious and quantitatively inclined student. She wanted to learn calculus and German because that's what you needed to know if you were going to be a professional scientist. She, of course, got pushback because ladies supposedly didn't need to know such things. After she completed basically the British equivalent of her K through 12 education, she went on to study at Newnham College, the women's college at Cambridge, even though Cambridge, like basically everywhere else in the UK, didn't award degrees to women. You could kind of get a piece of paper that said you did well enough on your exams to get a degree, but since you're a woman, we're not going to give one to you. Her time at Cambridge, though, was nevertheless transformational. When she arrived, Payne intended to study botany, physics, and chemistry. When she was young, she apparently won some kind of contest, and the prize was a book, and she chose a book on fungi, much to everyone's chagrin. So that's kind of what she was interested in at the time. But just by happenstance, she attended a lecture by one of the eminent physicists of his day, Arthur Eddington. He discussed his solar eclipse expedition to West Africa, where he conducted a test of what was then the still new theory of general relativity. She wrote later in her autobiography that when she returned home after the lecture, she wrote the lecture down from memory and that it completely turned her world upside down. She says she didn't sleep for several days. She immediately changed her focus to physics and astronomy. So this was a time when the suffrage movement was gaining momentum in both the US and the UK, but Payne still faced an uphill battle in her studies. Studying physics isn't easy, even if you have all the social support in the world. But as a woman blazing a trail in this male-dominated college and field, it was something else. Payne was like almost ritually humiliated by her professors. At the time, there was a requirement at Cambridge that women were to sit at the front of any class they attended. So Payne took a class from Ernest Rutherford, who was making huge strides in the fields of atomic and subatomic physics. His breakthroughs are still taught in physics classrooms today. And every class period, he would go out of his way to humiliate Cecilia Payne. So this is a quote from her autobiography. At every lecture, Rutherford would gaze at me pointedly and would begin with his stentorian voice, "Ladies and gentlemen." All the boys regularly greeted this witticism with thunderous applause and stamping with their feet. At every lecture, I wished I could sink into the earth. To this day, I instinctively take my place as far back as possible in a lecture room. So Ernest Rutherford was a real class act. However, she received much encouragement from none other than Sir Arthur Eddington himself, who changed her life with that lecture. He engaged Payne in his work on the structure of stars, but also warned her that if she wanted to be an astronomer, she needed to leave England. There were basically no opportunities for an astronomer who is also a woman there. Cambridge, remember, wouldn't even award women a real undergraduate degree. So getting an advanced degree in the UK was pretty much out of the question. So this seems bad, right? When someone who seems to believe in your ability and your talent tells you that you basically have no professional future in the country of your birth. That's not great, but all is not lost. Payne met an astronomer named Harlow Shapley when Shapley was in the UK giving a talk at Cambridge. Shapley just so happened to be the director of the Harvard Observatory, and Payne learned that he was starting a graduate program in astronomy at Harvard. With a glowing recommendation from Eddington, Shapley offered Payne a fellowship earmarked specifically for women to study astronomy, which included a small stipend. All Payne had to do was get to the US, which easier said than done. Payne received a little money from Newnham College, and as just a small example of her grit and determination, she entered an essay contest writing about the Greek text of one of the books of the Bible, right? So this is not her area of expertise. But it was an obscure contest, and Payne was betting on few people entering, and that bet paid off. No one else entered, and she won £50, giving her enough money to make the trip to the US and continue her education. So on your screen right now is an image. This is Cecilia Payne traveling to the United States. But even in her travels, she couldn't outrun gender discrimination. Shapley wanted the chair of Harvard's physics department to sign off on Payne's PhD, but they wouldn't accept a woman PhD candidate. Harvard, like Cambridge, also didn't officially admit women. So Shapley arranged for Payne's graduate work to be done technically at Radcliffe College, which was the women's college at Harvard. Most of her research work, though, was done at the Harvard Observatory, and it's work that she started in 1923. So she was around 22 or 23 years old at this point. And within a couple of years, Cecilia Payne will have made one of the most consequential discoveries in all of astronomy that still reverberates today. So this is an image here taken on the observatory grounds around 1924. And this is Payne right here, along with two other women who worked at the observatory at the time, Harvia Wilson and Adelaide Ames. So I want to stop at this point in her story because it's important to understand the scientific landscape in which Payne finds herself. So the early 1900s were a time of rapid advancement in our understanding of physics and consequently our understanding of astronomy. Specifically, Payne's work would not have been possible without the work of another woman at the Harvard Observatory, Annie Jump Cannon, who worked on classifying stars by their spectra, and a Bengali Indian astrophysicist called Meghnad Saha. But first, to study stars, one needs to understand electromagnetic radiation, which is really just another term for light. So light, we typically measure it as a wave, and it gets measured in wavelengths. Kind of like a water wave, right? The distance from one peak to the next peak is one wavelength. The shorter the wavelength, the more energetic the light. And these wavelengths, they span a huge range. The wavelength of the least energetic light, so radio waves over on this side, can be hundreds of kilometers long, while the wavelengths of the most energetic light over here, gamma rays, they're a fraction of a nanometer. Visible light, light that we can see with our eyes, takes up just a small fraction of the electromagnetic spectrum, kind of between around 400 to 700 nanometers. But all of these wavelengths taken together make up the electromagnetic spectrum. We can measure the spectrum with a device called a spectrometer. It's kind of like we can use a prism or something similar to kind of smear out the light so we can detect different wavelengths. So this is what happens with visible light when it passes through a prism that might hang in your window, for example. Each wavelength of light bends at a slightly different angle, which separates out the different colors to make that rainbow of visible light. So this same principle works with non-visible light as well. So spectra can be represented in a couple of different ways. It can kind of look like a barcode, like these images right here, or a line graph. So you have these corresponding line graphs underneath the barcode image on your screen. So where the light is intense, we call it like an emission line. So right here, we have little spikes. These are emission lines. And where it's not intense, kind of have reverse spikes. They go down like this. For the barcode image, the light regions represent where we can see light, and the dark regions show where light is not seen, right? For a line graph, those correspond with those peaks or those valleys, depending on what type of spectrum you are looking at. So why does the electromagnetic spectrum look like this, right? Like, what does it tell us? So measuring a spectrum like this can actually tell us what kind of material we're looking at. Every atom has its own spectrum, like a fingerprint. This unique fingerprint is caused by the number of protons in the atom and the configuration of the electrons. So we have this image at the top of your screen. It's the periodic table, but in spectra. And you can see each one of these elements has a unique configuration of light and dark stripes. It is truly like their fingerprint. So here comes the part where we realize that to understand huge things like stars, we need to understand very tiny things like atoms. At this time in the early 1900s, we're seeing the development of quantum theory, the physics theory of very small things. So Niels Bohr presented a view of the atom in 1913, in which the atom is a dense, positively charged nucleus surrounded by a cloud of electrons. And up here at the top of your screen, you see some of his scribbled notes on the subject, impenetrable. According to quantum theory, atoms and molecules can absorb energy, absorb light, and become excited. To become excited, an electron that is bound to an atom must jump to a higher energy level. So here's where things can get a little bit complicated. An electron can't simply absorb any amount of energy and become excited. Each energy level requires a precise amount of energy to get there, no more, no less. An electron must absorb a photon with the exact right amount of energy to jump an energy level. Energy levels are also sometimes called energy states. Light, as we've seen, is a wave measured in wavelengths, but it can also be thought of as a photon, which is like a particle of light. These photons exist at discrete energies depending on the wavelength given by this equation here. So the energy of the photon, the energy E, is basically inversely proportional to lambda, which is the symbol for wavelength. So the higher the wave, the bigger the wavelength means the lower the energy, right? Radio waves have less energy than gamma rays. If a photon doesn't have the exact right energy to boost an electron up an energy level, the electron will tend to simply not absorb that photon. This ends up being a really important fact, so I want to linger on it a little bit longer. In quantum theory, electrons need to absorb the right amount of energy that will allow the electron to jump directly from one energy level to another. So let's look at hydrogen as an example. It's a simple element. Let's say we have a hydrogen atom in its lowest energy level. So we call it its ground state, or its n=1 energy level. So in this diagram here, that's right down here. To jump from the ground state to the second, or the n=2 energy level, takes 10.2 eV, or 10.2 electron volts of energy, which is just a unit of energy. So we need a photon that is 10.2 eV. If we want to jump from the n=2 energy level to maybe the n=4 energy level, which we can do, we can skip over n=3, we only need 2.55 eV of energy. So we need a photon with the energy 2.55 eV. If an electron and a photon don't kind of match up in this way, the electron is not going to absorb the photon, and the photon will kind of just pass right through. This process of electrons absorbing light at specific wavelengths causes these absorption lines, these dips or dark spots in the spectrum. So on this image here, you have absorption lines, these dark spots in the spectra, kind of the dark lines on the bright background are absorption lines. Right, because the electron is absorbed by the photon, or the electron absorbed the photon, excuse me, the light is not available to reach our detectors, so it will show up as a dark patch in the spectrum. There's an inverse process as well, when an electron will de-excite, when it will drop an energy level or two. And so when this happens, a photon of the exact same energy as the difference between the energy levels will be emitted. And these are emission lines, and those are the peaks in the line graph, or they are the bright spots on the dark background of one of these barcode images right here. Some of the most important spectral lines in astronomy are called Balmer lines, or the Balmer series. These are spectral features of hydrogen that show up in the visible wavelength, so they're kind of easier for us to see. The Balmer series consists of 4 main lines. At 410 nanometers, we see that in the violet. 434 nanometers, which is blue. 486 nanometers, which is kind of this teal or this blue-green. And then at 656 nanometers, it shows up in the red. So these lines from red to violet are called H alpha, H beta, H gamma, and H delta. The H standing for hydrogen, and the alpha, beta, gamma, and delta just to tell the lines apart. And they all involve transitions either from the second energy level to a higher level or a higher level down to the second energy level. The Balmer series can be emission or absorption lines, depending on the properties of what you're looking at. But for stars, they're usually absorption lines. So that's how I will talk about them. So H alpha involves a transition from the second to the third energy level. So it's absorbing a photon with enough energy to get to the third energy level. H beta involves a transition from the second to the fourth energy level. H gamma goes from the second straight to the fifth, and H delta goes from the second to the sixth energy level. So these absorption lines prove to be integral in classifying stars. Remember, we can think of the spectra of atoms and molecules like a fingerprint. So if we're looking at a star and we don't see the spectra of a certain element, does that mean that the element isn't there? Well, unfortunately, it's not that simple, because sometimes an atom can get so excited that one or more electrons are fully stripped from the atom, right? We say the atom has become ionized. So on the screen here is an example of how this might look for hydrogen. If there are photons of the right energy that energize an electron enough, the electron can become unbound from the rest of the atom. So in this case, in the case of hydrogen, an ionized hydrogen atom is just a hydrogen nucleus, which is just a proton, and then it's a free electron that is unbound to the nucleus of the atom. You can see ionization in action if you ever see an aurora, right? An aurora is basically ionization of the atmosphere. As the temperature of a gas rises, atoms will move around more rapidly. Atoms will be more likely to be in an excited state, but they are also more likely to be ionized. If an atom is ionized, it doesn't have the electrons needed to absorb photons. So even though an element is there, we won't necessarily see the spectral features if most of it is ionized. So this is a genuine conundrum, right? But an Indian astrophysicist named Meghnad Saha made an important connection. He developed an equation that linked the fraction of ionized to neutral atoms with temperature and density. So right here, it's the fraction of the ionized atoms of a species with the neutral atoms of the same species. So the atom's kind of intact with all of its electrons. This ratio is proportional to the temperature. Astronomy students learn this today as the Saha equation. It shows that if a gas is too hot, atoms will be ionized and they cannot absorb photons. More than that, his equation can be solved to tell us at what temperature you expect to ionize whatever element you are analyzing. This is important because it shows that just because you don't see strong spectral lines doesn't mean that there's not a lot of that element there. It could be that the temperature for it just isn't right. Before we had this theoretical idea that spectral lines were linked very intimately with temperature, many efforts were underway to classify what we see in the universe. I mean, this is really an ongoing project, but there was a real concerted effort in the 1800s to classify stars, and much of that work was done at the Harvard Observatory. The stellar classification system we use today was developed by Annie Jump Cannon, one of the women known as the Harvard computers. And these women did precision analysis of astronomical data and made huge contributions to astronomy. So at the time, there was disagreement on whether or not the classification scheme for stars should be very detailed and complex and take into account every little nuance, or something more simple and straightforward that just kind of caught broad categories of stars. Cannon found a middle ground. So there was already in existence a classification scheme that divided stars into groups A through Q based on the shape and features of a star's spectrum. Cannon realized that this was simply way too many groups. There were way too many groups. There was significant overlap. So to classify stars, Cannon looked primarily at the strength of their absorption lines and their Balmer lines in particular. So Cannon took this complicated system, eliminated redundant groups and reordered groups to add more continuity between the spectral lines. And the result is what today we call the Harvard classification scheme. Stars are classified as either O, B, A, F, G, K, or M. To remember them in that order, I use the mnemonic, "Oh boy, a furious goat kicked me." Works for me, your mileage may vary, but I like it. What was so powerful about Cannon's system is that it is predictive, as shown by two astronomers working independently in the early 1910s. So Einhard Hertzsprung and Henry Norris Russell both related how bright a star is, its absolute magnitude, to its spectral class. So this ends up being a pretty powerful tool for the stellar astrophysicist. If you can figure out a star's spectral type, whether it's an O, B, A, F, G, K, or M star, you can figure out how bright the star is, not how bright the star looks, which is dependent on our distance from it and is often unknown, but how bright the star actually is. Once you know how bright the star is, you're just a couple of relatively simple calculations away from knowing how far away the star is. So this diagram on the screen relates the brightness of the star to its spectral type. So it's called the Hertzsprung-Russell diagram, or the HR diagram, and you have its brightness or its absolute magnitude on the y-axis and its spectral type down along the x-axis. And the true power of the HR diagram, though, was not revealed until Cecilia Payne decided to do an unbelievably detailed analysis on the atmosphere of stars. Okay, so the last time we saw Cecilia Payne, she had just arrived at the Harvard Observatory, ready to get to work. Her plan was to study the spectra of the atmospheres of stars in detail, and she honestly could not have chosen a better place. The Harvard Observatory had an archive of hundreds of thousands of stars that needed studied. And you can see here, these are an example of how spectra was actually recorded. They're recorded on these giant glass photographic plates. You can see here in this image, several stars have been classified by the spectra that was kind of read with magnifying glasses. It was truly a feat. So at Cambridge, Payne had studied this new field of quantum physics, and she brought this expertise into her research on stellar atmospheres. She knew all about atoms and that the reasons we see dark lines in the spectrum is due to the configuration of electrons in the atom. She also knew that at high temperatures, atoms can be stripped of their electrons. They can become ionized. She also knew that the spectrum of an ionized atom will look different from the spectrum of that same species as a neutral atom, an atom with all its electrons. She was familiar with the Saha equation, which had only been published just really a few years before. She was really on top of the cutting edge physics. And she knew that she could use it to understand the atmospheres of stars. Payne set out to measure 18 different absorption lines in the spectra of stars. She applied these most cutting edge theories, like the Saha equation, to the Harvard Observatory's vast and unmatched collection of stellar spectra. She related the spectral lines to the temperature of the stars and managed to determine the abundance of each of the 18 elements, or how much of each of the 18 elements she studied existed in the stars that she studied. In her thesis, she made two main findings, honestly, either one of which would have made a fantastic thesis in and of itself. So first, she determined quantitatively that the stellar classification scheme developed by Annie Jump Cannon is in fact also a temperature scale. O and B stars are the hottest, K and M stars are the coolest. Now, not only can you tell distance from the HR diagram, but you can also tell temperature, which opens up whole new avenues for stellar astrophysics. It was suspected that the stellar classification scheme had something to do with temperature, but Payne showed for the first time that it was, and she showed it quantitatively and without a doubt. So on the top left here is the table from Payne's thesis showing how temperature corresponds with spectral class. She starts with the M class stars, shows that these stars have relatively cooler temperatures, and she goes all the way to O stars, which have much higher temperatures. On the bottom right is a version of the HR diagram with temperature across the axis at the top. You can see these M-class stars correspond to about 3,000 Kelvin. O stars were up here about 25,000 to 30,000 Kelvin. So the lower left shows basically what the temperature range is that we typically associate with the different spectral classes. You can see O-type stars are the warmest star, get progressively cooler until you get to the M-class stars, where we have they're about 2,000 degrees. And like I said, this probably would have been enough for a PhD thesis. This was a great thing for stellar astrophysicists to know. It was something that had been suspected for a while, but not proven. But it's her second finding that was the big bombshell, the one that everyone remembers. So after determining that Cannon's scheme was actually a temperature scale, she used the Saha equation to determine the abundance of the 18 elements. She found that stars across the board are made almost entirely of hydrogen and helium, with essentially just trace amounts of everything else. So right here, this is the table that Payne included in her thesis, showing the measured abundances, that's the log AR, of hydrogen and helium are overwhelmingly more abundant than the abundances of everything else that she studied. Now, this to our 2023 ears maybe sounds very obvious. Like, of course, stars are made of hydrogen and helium. But this is nearly unheard of in Payne's day. This is a complete reversal of what we thought the universe was made of. At the time, it was assumed by every serious astronomer that the sun and the stars are made up of basically the same things that made up Earth. The Earth is rocky. There's a lot of oxygen and silicon and aluminum and iron. And importantly, there is not very much hydrogen and helium. And so the assumption was that stars were made of stuff like this too. And they are a little. There's just a million times more hydrogen and helium than anything else. We were wrong about the proportions of what elements were in the stars. These results did not go over extremely well. So Payne's advisor, Harlow Shapley, sent her thesis to an astronomer, Henry Norris Russell, so the same guy who helped develop the Hertzsprung-Russell diagram, who was also a big proponent of the idea that stars are made of the same stuff as Earth. So in a letter to Payne, he wrote, "There remains one very much more serious discrepancy, namely that for hydrogen, helium, and oxygen. Here I am convinced that there is something seriously wrong with the present theory. It is clearly impossible that hydrogen should be a million times more abundant than the metals." Metals, by the way, is astronomer speak for everything in the periodic table that isn't hydrogen and helium. So Russell also happened to be on the committee that stood in between Payne and her PhD, her degree. And the reality was, despite her detailed calculations and careful analysis, no one believed that stars were made of mostly hydrogen and helium. In order to be awarded her PhD, Payne felt that she had to kind of disown or at least distance herself a little from her own results, writing in her thesis that the percentages of hydrogen and helium were spurious, improbably high, and therefore almost certainly not real. This was something that she says she regretted. She wrote in her autobiography, "I was to blame for not having pressed my point. I had given into authority when I believed I was right. I note it here as a warning to the young. If you are sure of your facts, you should defend your position." So she may have blamed herself, but I personally do not blame her at all, right? This was a time when women were nearly non-existent in the field. The Harvard Observatory was really a fantastic exception. But they weren't common, and there were powerful men standing in the way of a career that she really wanted more than anything. And she did what she had to do, right? She didn't take the data out of her thesis. She left it there for people to judge on its own merits, which they do, and she is later vindicated. And yes, to be extremely clear, she was correct. Even Henry Norris Russell, one of her most vocal critics, had to agree with her eventually. He came to the same conclusion using other methods only a few years later. He cited her thesis in his paper on the subject. So this is the table that was in Russell's paper on the composition of the sun's atmosphere. He makes direct comparison between his measurements of the abundance of elements in the sun and Payne's measurements published in her thesis. So you can see here we have columns for the different elements. Miss Payne's, her measurements of the abundances. This column here is Russell's own measurements, and you can see the difference. And they match remarkably well. Russell's study was on the sun only, and Payne's was many different stars. But you can see the sun is a star, and their measurements of the abundances are pretty consistent with each other, which is a vindication for Payne. Payne's PhD thesis was a borderline heroic work that took place only over the course of a couple of years. She was in her mid-20s and she had shaken our understanding of the universe. But even field-shattering PhDs need a job after they graduate, and Payne was hired on at the Harvard Observatory as a technical assistant, a position to which she was way overqualified. She joined the ranks officially of the rest of the Harvard computers. So when she was a graduate fellow, she was free to choose her own research projects. But as a very lowly paid technical assistant, she had projects assigned to her. And these projects tended to be extremely repetitive and not very intellectually stimulating for Payne. Shapley believed in her intellect, though, and had her teaching graduate level astronomy classes, but without the title of professor or even instructor. When Shapley approached the president of Harvard, Abbott Lawrence Lowell, about this, Lowell said that a woman would never have a position at the university as long as he was alive. Harvard wouldn't even list her courses. For years, they wouldn't list her courses. Shapley even wanted Payne to be the first chair of the newly formed astronomy department at Harvard, but knowing that a woman would never be approved for this position, offered the job to a man instead. So for a long time, Payne was in this kind of professional limbo. She was an extremely poorly paid technical assistant without an academic position, yet she was still publishing books. She published hundreds of research papers and was an extremely popular instructor. Everybody knew how brilliant she was, and yet she was just kind of stuck in this role that she couldn't seem to get out of. And this went on for decades. This is, though, I am very pleased to report, not a story of a genius who was not recognized in her own time. Payne eventually gets her due. So when Shapley retires as director of the Harvard Observatory in 1954, Donald Menzel took over. He found out how little Payne was being paid and immediately doubled her salary. And with Lowell, the Harvard president who swore he would never hire a woman, out of the way, he had also since retired, Menzel was able to get Payne promoted to full professor of astronomy in 1956. This was such a big deal that it was reported in the New York Times. A few months later, she was named as chair of the astronomy department, the first woman to chair a department at Harvard. In 1976, just a few years before her death, she received the Henry Norris Russell Lectureship Award from the American Astronomical Society, an award named after the very person who vehemently opposed her groundbreaking thesis result. This award is quite prestigious and is given in recognition of a lifetime of achievements in astronomy. At this point, everyone recognized that Payne was correct, that stars are made of hydrogen, and appreciated what an achievement that discovery was. A previous recipient of the Henry Norris Russell Lectureship, Otto Struve, called Payne's thesis on stellar atmospheres, quote, the most brilliant PhD thesis ever written in astronomy. She's won the Rittenhouse Medal for Achievement in Astronomy. She was the first recipient of the Annie Jump Cannon Award in Astronomy, and several awards are just now straight up named for her. Her name also graces an asteroid and a volcano on Venus. So I'm glad to say that despite the kind of overt misogyny she experienced throughout her career, she was recognized during her lifetime as one of the most brilliant and creative astronomers in the 20th century. The journal Physics Today said about her, quote, "She may have felt that she walked with giants. Now we recognize that she herself was one." And another journal, the American Physical Society News, said, quote, "The giants, Copernicus, Newton, and Einstein, each in his turn brought a new view of the universe. Payne's discovery of the cosmic abundance of the elements did no less." And I've actually said nothing so far about her personal life, but she is one of the very few women of her time who married and continued working. She was a professional astronomer up until the end. She married a Soviet astronomer named Sergei Gaposhkin in 1934 after helping him flee from Nazi Germany. They raised 3 children together, were reportedly very happy, and frequent collaborators on scientific projects. So this is Sergei and Cecilia, 1979, I believe, not long before Cecilia Payne dies. And here we have Cecilia Payne, her husband, and 2 of their children in her office, taken in 1946. Reportedly, her 3 children would run around the observatory, and not everybody was too happy about that. But how do you confront one of the scientific greats, Cecilia Payne? So Cecilia Payne, she was an incredible scientist with an unquenchable thirst for knowledge. That desire to understand why and to get to the bottom of the mysteries of the universe led to one of the most consequential discoveries in the history of astronomy. And she did this in the face of daunting obstacles. She wrote in her autobiography, "I had once pictured myself as a rebel against the feminine role, but in this I was wrong. My rebellion was against being thought and treated as inferior." I don't think that at the end of her life, anyone thought she was inferior to anyone. She persevered and quite literally discovered the stars. Thank you so much for being with me today. Next month, December, I will review a year of astronomy news. There were some big discoveries and interesting results from a variety of projects in 2023, and I cannot wait to talk about them with you. I'll see you then.